Hi everyone, in this video we're going to be looking at some of the many applications of matrices, and the first one that we'll be looking at is in terms of linear transformation. Okay, so a matrix acts on a vector. For example, if we have a matrix like 0, -1, 1, 0 acting on a vector, say x in, y in, then what this is going to give us, if we multiply this matrix by that vector, we're going to get minus y here and then positive x over there, right? So let's use real values for our x and y. If we can choose any values at all that we want. 0 here. All right. Let's use the values 1, 2. Okay, so this was going to give us, if we multiply, this is going to give us minus 2 and 1. Okay, so if we sketch these, right, this being our x-axis, this being our y-axis, then for our original vector we had 1 here, 2 there. Okay, so this is going to be 1, 2. All right, now after acting matrix on the vector, we had, use a different color code, we had -2. All right, so we have -2 and then 1. Okay, so this is going to be our new vector, -2 and 1. Now studying this closely, you realize that what this matrix does is to transform or to rotate our vector through an angle of 90 degrees anti-clockwise. That is what this matrix does. Okay, so we can look at another example of a linear transformation. So for example, if we have another matrix like 2, 0, 0, 2 acting on our vector x in, y in, okay, following the rules of multiplication of matrices, this is going to give us 2 of x, and then here will be 2 of y. Okay, if you pull out 2, or if you factorize 2, you're going to have 2 out and then x here and y here. So what this matrix does is to increase the length scale of vector x and y by a factor of 2. Okay, so for example, if we use the same vector that we used earlier on, we have 2 here, 0 there, 0, 2, on 1, 2. This is going to give us 2 out, 1 and 2. If we use 3, 0, 0, 3, on 1, 2, this is going to give us 3 out, 1 and 2. Okay, so if we are to sketch this, x here and then our y up there. Okay, so if this were to be our first vector, 1, 2, all right, then for the second is being stretched out by a factor of 2, so this is going to be 2, 4, and the third is being stretched out by a factor of 3, so this is going to be 3, 6. Right, so what this matrix does is that it stretches out the length scale of your vector, and the first one is to rotate it. So this is a scalar, and then the first one is by rotation. Now another way of using matrices to solve some problems is in terms of linear equations. Okay, so for example, if we have a system of linear equations such as ax plus by is equal to c, dx plus my is equal to f, then instead of using either the elimination method or the substitution method or the graphical approach, we can also use inverses of matrices to find a solution to this system. So to be able to do that, we need to know what is known as the coefficient matrix. and the coefficient matrix is depending on the type of system that you have, is a square matrix whose entries represent the coefficients in your system, followed by the vector that carries the variables in your system, and then the output vector, which corresponds to the constants after the equality sign. Right, so to be able to use inverse of matrices to do this, we first of all find our coefficient matrix. Okay, so before we can do that, we need to make sure that all our variables are in line. So if your first variable is x, then it means in the first equation, then it means the first variable in the second equation must also be x, followed by y, and then followed by y in the second equation, and so on. Okay, so to be able to do that, you need to make sure that the variables are in line. Then to construct a coefficient matrix, just simply write all the coefficients in your system. So this becomes A, B, I have D here, and M. Alright, multiplying the vector that contains the variables, and the variables are x and y. This is equal to the output vector, and the output vector is the constant after the equality sign. So this is what is known as the matrix equation. So if you're being asked to put a system into a matrix equation form, it means look for the coefficient matrix, which is the coefficient in your system multiplied by the variables in your system equals to the output vector. Okay, so now let's label our matrices and a vector here. Let's call the coefficient matrix x. Let's call the vector xy as x. So our coefficient matrix as A, our vector xy as x, and then the output vector as b. Alright, these are vectors, so let me put the arrow on the top. Alright, now what are we looking for is the values of x and y, which has been put into the vector x. So to look for x and y, we need to make sure that we make x the subject. Right, now these are matrices. We can just simply divide both sides by a, and then make sure that x is standing alone. So what you do is to use manipulation using inverse of matrices. Alright, so if A is a matrix, then A times A inverse is equal to A inverse times A, and this is the identity matrix. Okay, so to be able to do that, we multiply both sides by A inverse to get rid of the A, and you do left multiplication. Okay, so A inverse times A times x. Okay, this is equal to A inverse times the vector b. Right, so at the end you have A inverse times A times x. This is equal to A inverse times the vector b. Now A inverse times A is the identity matrix times the vector x. This is equal to A inverse times the vector b. Now the identity matrix times any other appropriately sized matrix gives you the same matrix. Right, so this is going to be x is equal to A inverse times b. And so to be able to find a solution to your system, you multiply the inverse of the coefficient matrix by the output vector, and that gives you the values of x and y. So let's look at an example. We have a system giving us 3x minus 2y is equal to 1. We have minus x plus 4y is equal to 3. Now to be able to get a solution to this system without using the graphical or the substitution or the elimination method, and we want to use inverse of matrices, and first of all we need to make sure that all our variables are in line. Okay, so in the first equation x is the first variable followed by the y, and in the second equation x is the first variable followed by the y, so it means you don't need to do any rearrangement here. Right, so we can go straight ahead and then construct our coefficient matrix multiplied by the vector xy, and this is equal to the output vector that contains the constants 1 and 3. Right, so what are my coefficients? What are the components of the coefficient matrix? We have 3. For the y part we have minus 2, Then we come to the second equation, minus 1, and we have 4 here. Okay, so we label this as A multiplying the vector x is equal to the vector b. Now we've been able to deduce that if we have our matrix equation in this form, then x bar is equal to A inverse times the vector b. Okay, so to get our x and y, this is equal to 3 minus 2 minus 1, 4 inverse times 1, 3. Okay, so we find the inverse of that square matrix. Okay, we can do an aside work here. To find the inverse, we find the determinant, which is 12 minus 2. This is equal to 10. All right, the adjoint, this is equal to 4, 3, 2, 1. Therefore, A inverse is equal to 4 over 10, 2 over 10, 1 over 10, and 3 over 10. Okay, so this is equal to 4 over 10, 2 over 10, 1 over 10, and then we have 3 over 10 multiplying 1 and 3. Okay, so this is equal to 4 over 10 multiplies 1, that will be 4 over 10 plus 6 over 10. Then we pick the second row, we have 1 over 10 plus 9 over 10, and this is equal to 1 and 1. Right, so the value for x is 1 and the value for y is also 1. Now, to be able to know that these are the true values of x and y, we substitute these values into both equations, and if it checks out, then it means that is the correct solution to the system. So if we put these values in the first equation, we have 3 times 1 minus 2 times 1. We have 3 minus 2, which is 1. Okay, so for the first equation, it gets satisfied. Then we look at for the second equation, minus 1 plus 4 times 1. Okay, so we have minus 1 plus 4, and this is equal to 3. So for the second equation, everything checks out. So that is one of the many applications of matrices. Another way of using matrices is to study network or graph theory. So a graph could represent a lot of things. For example, the connection between a group of friends, the connection between a class or a group of friends in a class, your friends on Facebook and who you're friends with, your mutual friends, connections on dating app, a network of cities. You can also talk about websites and how they're connected to other websites. All right, so for a smaller network, all right, it's easier to understand what is happening or what's going on in that network. So for example, a small group of people or friends in a class, it's easier to understand what is going on within that network. But when the network becomes chaotic or too robust, then it's difficult to understand what's going on just by looking at it. Okay, so for example, if we have a network like right, let's draw a simple network here. Let's call this person A, B, C, D. Person E here. Okay. There's a network of small groups of friends in a class. About 10 or 11 of them. Okay. Then we could also have another one connected to this. Alright, so we call this M, X, U, W. Alright, now it's easier to understand what's going on in this network, alright, because it's simple. And I must also say that this network is not directed. It's not a directed network or directed graph. So A to M is the same as M to A. Okay, but if I put a direction on it, then it means I can move from A to M, but I can't move from M to A, right? So there's no direction on my network. Okay, so it's a simple one. Now, when it becomes chaotic, then it's difficult to understand it. And one of the simplest way to understand a chaotic network is to use matrices, right? And the type of matrix that we use to understand it is known as the adjacency matrix. And the adjacency matrix is a square matrix whose components represent the number of links between two nodes. Okay, so if we are to look at a simple network, like this, okay, and then we'll put another one here, put this one here, put another one here, and this one here. Okay, so I'm gonna call it A, B, C, D, E, F. All right, so let's consider this simple network of group of students in a class. Okay, to be able to understand what is really going on in here, we can construct the adjacency matrix to be able to understand what's happening in here. Okay, so I said the adjacency matrix it's a square matrix whose components represent the number of links between two nodes. Okay, so to be able to do that, we write down all the nodes in our network. All right, so A, B, C, D, E, F. We have A, B, C, D, E, and then F here. All right, so we go to our network. From A to A, how many links takes me from A to A? Now, if you look at it carefully, there is no link that takes you from A to A. If there is a link that takes you, or an edge that takes you from A to A, then that kind of link is known as a loop. Okay, so for example, if I have a node here and I have a link that takes me from A back to A, then this is known as a loop. But there is no loop in my system or in my network. Therefore, A to A is going to be equal to 0. Right? Then A to B, there is no link that takes me from A to B. Therefore, from A to B is going to be 0. Now remember, I said this network is not directed, so A to B is the same as B to A. And so if A to B is equal to 0, then B to A is also going to be equal to 0. Now A to C, there is no link between or an edge that takes me from A to C. And therefore over there too I get 0. And so here too will be 0. Right, then A to D, I have one link that takes me from A to B, so A to D, which is this link right here. It takes me from A to D, and therefore what we put over there is only one link, right? So I put 1 there. Then D to A will also get a 1 over there. Then A to E, I have 1. A to 1 will be here too. A to F is 1. Therefore, F to A will also be 1. Then we move on to node B. All right, B to B, there is no loop at B to B, and so I'm going to have 0 here. B to C, there's no link between B to C, so I have 0. Therefore, C to B to will also be 0. Then I have B to D. I have 1 over there. Therefore, D to B, I'll have 1 here. B to E, I have 1. So 1 will be here. Then B to F, there's no link between B and F, so I have 0 here, and therefore a 0 there. All right, then we'll move on to C. C to C, there's no loop, so I have 0. Then I have C to D, there's none there. Therefore, D to C2 will be 0 here. Then C to E, there's no link, 0, and so I'll have 0 here. Then C to F, I have 1, and so C to F, F to C, I also have 1 there. Okay, then we move on to D. Okay, D is connected to, okay, so let's move step by step. D to D, there's no loop, so I have 0. Then D to E, there's no link over there, so I have 0 here, therefore I'll have 0 there. Then we have D to F. D to F, there is none. Alright, so I have 0 here, therefore 0 there. Then we go to E. We have E to E, there's no loop, I have 0. E to F, there is none, so I have 0 here, therefore 0 there. Now we're left with F to F, there's no loop in our system, so I'm going to have a 0 here. Now this is what is known as the adjacency matrix that represents this network. Now the adjacency matrix also tells us the number of paths of length 1 in our network. Okay, the number of paths of length 1 that exists in our network. So if I want to know the number of paths of length 2, then all that I need to do is to square my adjacency matrix. Alright, so let me call this adjacency matrix capital A. Right now, bear in mind this A is different from node A. This A is this A here represents the adjacency matrix, and this A here represents the node A. Okay, so A tells us the length of the walks or paths of length 1 in your network. And so if we square A, that will give us walks or paths of length 2. And therefore, if I want to know the number of walks or paths of length 3, all I need to do is to cube it. Okay, so if I cube my adjacency matrix, so if I square my adjacency matrix, now over here you can do the pencil and paper approach, that is the hard way. You can also use Excel, you can use Python to do that. All right, now when I do mine, I'm going to get 3, 2, 1, 0, 0, 0, 2, 2, 0, 0, 0, 0. Right, then I have 1, 0, 1, 0, 0, 0. I have 0 here, 0 there, 0. Please, you can use any tool at all to do the multiplication. All right, A squared is simply A times A. And if you've been following the lecture so far, by now you should know how to multiply 2 or more matrices. Alright, so this is what I have. Okay, so the diagonal entries represent the paths of length 2 that exist between a node and itself. Okay, so let me circle the diagonal. This is the diagonal entries, and that represents the paths of length 2 that exists between a node and itself. Okay, so if we go back to our network, then the 3 here represents all the paths of length 2 that exists between node A and back to itself. So if we go back to our network, you notice that all the paths of length 2 between A and A are A to D to A, that is 1. Then we have A to E back to A, we have 2. And there's A to F back to A, which represents the 3 over here. Okay, then the 2 over here represents the path of length 2, of 2 between node B and itself. Okay, and the paths are B to D to B, and then B to E back to B. Okay, so I want you to also interpret from this is node C to itself, this is node E to itself, so node D to itself, node E to itself, and then node F back to itself. So for tryout, please try and see if you can locate all the paths of length 2 between node C and itself, node D and itself, and then node E as well as node F and itself. And like I said earlier on, if I'm to cube this matrix, then that is going to give me all the paths or walks of length 3 that exists between a node or 2 or more nodes. Okay, so a cube is giving us a squared times a. All right, now this one too, you can use the pen and pencil approach. You can also use Python, or you can use Excel to do that. Right, so when you cube it, you have 460,665. Please do not be lazy. Okay, try your hands on it and see if you can get the same thing. 552,010,112. Then we have 651,221. I have 651,221, and the last one is 522,110. Okay, now for some reason, if we sum the trace, or if we find a trace of your matrix and we divide it by 6, that tells us the number of triangles in the network. Okay, so the trace of a cube divided by 6 gives us number of triangles in the network. Alright, so let's find a trace. We have 4 plus 4 plus 2 plus 2. That will give us 12 divided by 6, and this is equal to 2. It means there are only 2 triangles in our network. And if you go back to check, you notice that the triangles are A to D to B and back to A. That is one of the triangles. Then the next one is A to E to B. That is, and then back to A. That is also one of the triangles. Right. So that is what the cube of the adjacency matrix tells us. It tells us the number of walks or paths of length 3 that exists between a node and itself. Then that is the diagonal. All right, so the 6 here represents the number of walks of length 3 that exists between node A and node B. All right, then the 0 here represents the number of walks or paths of length 3 that exists between node A and then node C, and so on. And if you sum the diagonal entries and divide it by 6, that gives you the total number of triangles in your network or in your graph. So another area where matrices is applied is in encryption, specifically Hill cipher. Right, so Hill cipher was invented in 1929 based on linear algebra, and it was invented by Lester S. Hill, and it's a polygraphic substitution cipher. So what this kind of encryption does is it uses matrices and matrix multiplication to mix up plain text. All right, and each letter is represented by a number modulo. Since we're using the English alphabet, and there are 26 characters in the English alphabet, so it will be modulo 26. All right, so the more characters that you add, the higher the modulus. So for example, if we let 0 be equal to A, all right, then we can write down what we're going to be using for the encryption, right? So A, we have B, C, D, E, F, G, H, I. All right, now the caps and then the lower cases are all the same: J, K, L, M, N, O, P, Q, R, S, T, U, V, W, X, Y, Z. All right, so I have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. All right, now I'm going to use the space bar as 26. All right, so everything is going to be a modulus 27 because I've added another character to it. Right, so anything that I want to encrypt at all, I change that plain text into numbers and then use Hill cipher process to mix up the plain text, all right, into a different unreadable form. So for example, if I want to encrypt a message, now before you can even do this, you need a key, all right, a key matrix to be able to do the encryption. All right, so once you send, what you'll be sending is your encrypted message together with the key, so that when the person who is supposed to receive the message gets it, you'll be able to decrypt your message using the key. All right, so you need two things: you need the encrypting message and then you need the key. All right, so let's look at encrypting a message using a key. Let's call the key K is equal to 3275. Now the key that you pick must have two, it must be a square matrix 1, and it must also be an invertible matrix. So it means the inverse of that key matrix must exist. All right, it must be a square matrix as well, right? That's redundant because if it's not square, its inverse will not exist. And even within square matrices, not all square matrices have inverses. So it could be a square matrix, but just that the inverse will not exist. So make sure that the key that you're picking is a square matrix and its inverse exists, or it's an invertible matrix. All right. So let's look at trying to encrypt the message like attack at dawn. Now, to be able to encrypt this message, now first of all, we convert these characters into numbers. All right, we put it in a matrix form, and then you will lock it up with the key matrix, and that gives you the encrypted message. Okay, so first of all, your encrypting message, let's call it A. You lock it up with your encrypting message. All right, so you lock it up with your encrypting message, which is attack at dawn. Supposed to be the key. Then the encrypting message that will give you the encrypted message. Okay, so to be able to do this, we write down the attack at dawn into numbers form. All right, so A is 0. So I'm going to have, let's write them down one by one. Okay, so the entries are 0, 19, 19, 0. All right, then we have 2, 7, 26, 0, 26 because I have space over here, and I also have another space over here, which will correspond to another 26. Okay, so I have 19. I have 26, I have 3, I have 0, I have 23, and then I have 13. Okay, now the way we'll put this this set of numbers into a matrix form depends on the number of columns in our key, because if you look at the equation very well, it is the key multiplying the encrypting message. Right now, two matrices, the product is defined if and only if the number of columns in the first matrix is equal to the number of rows in the second matrix. All right, and so since the number of columns in our key is equal to 2, then it means that the number of rows in our encrypting matrix must be equal to 2. All right, so our encrypting matrix should have only 2 rows. Okay, so we're gonna put this into a 2 by something matrix. Okay, so I have how many entries here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Excellent. Right, so I have 14 entities. If I'm going to have 2 rows, then it means I'm going to have 7 columns. So when I reach the 7th number, I move on to the next row. So I have 0, 19, 19, 0, 2, 7, 26, which is the 7th number. All right, then I have 0, 19, 26, 3, 0, 22, and then 13. Okay, so we're gonna multiply the key by this encrypting matrix, and that will give us the encrypted matrix. Okay, so let's do that. We have k times a is 3275. All right, multiplying encrypting message, and that will give us our encrypted message. All right, so please do this any way that you can, whether you want to use Excel or you want to use Python. Remember, if you're using Excel to do multiplication, the function is mmult, and if you're using Python to do that, the function is mat.mul, matrix multiplication. So mat.mul into bracket the first matrix, comma the second matrix. All right, so if we do the multiplication, then we're going to have, if you're done, all right, doing it, then you set. Okay, so we have 0, 95, all right, 109, we have 6, 65, 104. Then the second row we have 0, 228, 263, 15, 14, 159, and 247. All right, now this, remember, is going to be in modulus 27, okay, because we had 27 characters in all. All right, so we're gonna have 0. Right, then the next one was 95 modulus 27, that will give us 14. Then the next one was 109 modulus 27 will give us 1. That's 6 and 6. 65 modulus 27 will give us 11. 104 modulus 27 will give us 23. So we have 0. 288 modulus 27 will give us 12. We have 20. We have 15, 14, 19, and then 4. Okay, and so now if we go back and compare these numbers to the system that we set earlier on for A, B, C up to Z, and then the space bar representing number 26, 0 is A. All right, so we have A here. 14 is O. All right, then we have 1 to be B, 6 to be G, so we have G. All right, then 11 was L, 23 is X, 0 is A, 12 is M, 20 is U, 15 is P, 14 is O, 19 is T, and 4 is E. All right, So the message that we were trying to send was attack at dawn. At the end of the day, this is what will be showing. All right, so we had K, which was our key, multiplying our encrypting message. This is equal to the encrypted message, which I'm going to call E. All right, now using the same approach that we use and using inverses to find a solution to a system of linear equation, I'm going to leave this to you as an exercise. Try and see if you can decrypt this message. All right, so to decrypt this message, it means to make sure that A is standing alone. All right, to make sure that A is standing alone, what do? Multiply this side by K inverse, okay, and then also this side by K inverse. Okay, so you end up having K inverse times K, that will give us I, times A is equal to K inverse times E. All right, therefore A is equal to K inverse times E. So to go back to the original attack at dawn, what you need to do is to multiply the inverse of your key, all right, which was given as 3275. Multiply the inverse of this key by the encrypted message, and that gives you back your encrypting message. Okay, so let's look at another example.